Great. Thanks, Suman. I appreciate it. While I bring up my slides, I just want to thank everybody for joining us and for your time listening to us talk about our energy storage systems. Can you see those slides now, Suman? Yeah.
Yes.
Okay. Okay. So, yeah, I'm the Chief Commercial Officer at Ambry. Been with the company about 5 years. Before that, about 35 years in other battery companies and technologies, including some well-known brands like Duracell, as well as companies in the large-scale energy storage space as NEC Energy Solutions, where I was Chief Commercial Officer 5 to 10 years ago. So now I'm going to talk about Ambry. Ambry is a brand new battery chemistry, uses novel materials, and it's aimed at purely stationary, large-scale energy storage. And, oops. So, so Ambry's batteries are ideally suited for the daily energy shifting market. By that, I mean, most classic example is charging the battery during the day when solar is generating energy, and using that to charge the battery so that it shifts that energy to the evening when the peak demand for electricity typically occurs. And you discharge the battery at night after solar has stopped generating, and repeat that process every day. You could do it twice a day if you so choose. And it all depends on the duration of your charging and your discharging as to how many of those you can squeeze into a day. Doesn't have to be 4 hours. 4 hours could be a charging over a 5-hour period, then discharging over 19 hours in order to get to, let's say, a 24-hour renewable generation situation. Anyway, Ambry's batteries are good for this because they are high temperature batteries. They like to be used heavily. They cost generally less than lithium-ion batteries, both at CapEx as well as OpEx, and clearly, therefore, over the total cost of ownership. They're a long lifetime battery, 20 plus years of usage, even with very minimal degradation. So our specification is no more than 5% degradation over those 20 years at one full cycle per day. Very safe technology. There's nothing flammable associated with it. Doesn't have a thermal runaway possibility. And the materials, as I mentioned earlier, are unique. We use calcium as the negative electrode in this battery, and we use antimony as the positive electrode in this battery. And we're not familiar with any other company doing any work with calcium antimony batteries. And one of the reasons that it's not common to see other people do that is that it's a high temperature battery system. And so it requires these materials to be heated up before they're useful as battery technologies, and I'll talk a little bit more about that. From a commercialization perspective, we have commissioned a system for the Microsoft's Advanced Data Center team last year. We've been testing that system. I'll show you a picture of that. We're about to launch a number of additional pilot systems beginning of next year through 2024. We'll be doing both single container systems, and then we'll be opening up a pilot manufacturing facility in Massachusetts, which will be completed in the middle of next year. Then we will be issuing a number of pilot systems of larger and larger scale through 24. And then in 2025, we'll be opening our high volume manufacturing plant, initially in the United States, and then we'll be expanding manufacturing into other regions around the world. Originally, the company was spun out of MIT. It was financed by Bill Gates for a number of years. And then recently we've raised capital from other sources, including Paulson & Company, Reliance Industries out of India, Fortistar, is a US energy investment. And this is basically what the product looks like. It's like a lot of other traditional batteries in that it has a cell. The cell is an enclosure, in our case, stainless steel enclosure. There are no moving parts associated with this battery system. So these are hermetically sealed cells, which we align next to each other on a tray or a shelf, as you can see here. And then we stack those shelves inside of a shipping container. We're planning on 20-foot shipping containers with about 1.1 megawatt hours of energy, and that's at the 4-hour charge and discharge rate. Like other batteries, if you operate the battery more slowly, so at lower power, you will get a longer duration. So you get 8 hours, 16 hours, 24 hours out of this exact same container. When you do that, you will typically get more energy out of that battery. So we'll get up to 1.3 megawatt hours out of the same container. We'll also get a higher efficiency. So it's 80% efficiency, round trip efficiency at a 4-hour rate, gets up to about 90% at a 16-hour rate. And that's just nothing unique about Ambry's batteries. It's just the nature of batteries tends to have that type of relationships between energy and capacity. As I said, it's a 20-year battery system. So what we do is we assemble and manufacture these systems all at room temperature. We ship them to a site, we install them, and then during the commissioning process, we connect to the grid. The grid electricity energizes heaters that are inside the container. That warms up the entire inside of that container up to its operating temperature. And then once it reaches operating temperature, that's when the batteries have a voltage. And that's when current, just charging and discharging current, can be moved in and out of the battery. Before that, actually these cells have no voltage. They cannot conduct electricity. They're essentially inert blocks of metal, which makes them quite safe in the manufacturing, shipping, installation process. But once we heat them up, they're ready to go. We can disconnect from the grid if needed. We don't need heating from that point forward. The whole process of charging and discharging generates heat, just like it does in your cell phone or in a lithium-ion battery for energy storage. The difference is we trap that heat. So there is thermal insulation on the interior walls of this container, and there is no HVAC system. So we are not trying to remove that heat, we're trying to contain that heat. And the nature of daily charging and discharging generates plenty of heat in order to keep the batteries at its operating temperature. It doesn't have to be every day, could be every other day type of charging and discharging, but we do want to see a full discharge cycle, charge cycle occur in order to keep that energy, that temperature up. It doesn't have to be all at once. It could be, let's say, doing frequency regulation or some other type of shallow charging and discharging. It's the net total or the throughput of energy that is necessary in order to generate the quantity of heat that's necessary to keep it warm. And as it so happens, the largest application for batteries on the grid, particularly long duration batteries, is to shift energy every day from typically middle of the day to the evening. And so that's the application that these batteries are best suited for. And as a result of them being lower cost, longer life, and low degradation compared to lithium ion, they're a better product than lithium ion. And that's what this is positioned against, even at the 4-hour duration level. This is the first pilot system that I talked about, which was done for Microsoft's data centers. So this is a 20-foot container. It actually only has about 264 cells in it, relatively small utilization of the space inside this container. You can see actually in the picture on the left, there are actually some open holes in it. The batteries are actually only in about the far left side of this battery. And looking in at that left side, this picture on the right, you can see essentially the trays or the shelves that have been inserted into this. There are 12 of them, and each of them has electronics. So we measure the voltage of each cell. That cell then is monitored for balancing on a real-time basis. We have a battery management system integrated into this container. So you can see the system can be operated with the doors open or closed. But of course, inside or behind these electronics, the temperature is high, and in not anticipated, we're going to open that system during the life of the system, and we're not going to service anything inside that system on a preventative basis. Now, Microsoft is looking to eliminate diesel generators, so they're looking at long duration energy storage instead of diesel generators, and the short duration batteries they use. They're looking to integrate renewable 24/7 in order to power their data centers. And lastly, batteries are higher reliability than engines, and therefore you get higher reliability as a benefit. Just a little bit more about the technology. As I said, calcium antimony. We heat those materials up in order to achieve a charging and discharge capability. Though we chose those materials because they're lower cost than lithium ion. We also chose them because the calcium does liquefy at the high temperature. We also have an electrolyte, which is primarily calcium chloride, that also turns into a liquid. As a result of those components liquefying, then we do get very low degradation. As a result of it, degradation is primarily a mechanical effect. We also, inside these cells, there is no ability for gas to be generated inside the cell. So the cell is hermetically sealed, has no vent. It is not vulnerable to short circuiting, overcharging, over discharging. None of those things generate gas or even cause any lack of safety inside the system. And I'll talk about that a little bit more. Typical cycle life curve of this technology. One interesting factor is that it does typically increase capacity over the first 1,000 cycles. That's a natural and understood behavior of these materials. Otherwise, from that point on, stays flat. We don't see degradation as a result of the usage of this chemistry. The materials are very strong from an environmental perspective. First of all, it's easy to recycle the materials or reuse them. In case of the cells, the stainless steel and the antimony are the only constituents that don't dissolve in water. So they're very easy to remove. There's about $35,000 of value from the stainless steel and the antimony in a megawatt hour of batteries. So there's about $35,000 of essentially positive value in order to pay for decommissioning. And then the other materials in the balance system, typically reusable, therefore creating a sort of economically motivation in order to recycle and reuse the materials at the end of life. And in addition, the life cycle analysis of these batteries is favorable to lithium ion. So about 70% more greenhouse gases are generated from the lithium ion industry than this technology. So that's taking consideration the mining of the materials, the transporting those materials, the building of the batteries, transporting the batteries, the using the batteries, and the decommissioning of the batteries for the total life cycle. So strong greenhouse gas throughout that whole process. I mentioned safety. Here's a little bit more detail on it. The UL 1973 safety test involves taking a battery and overcharging it, over discharging it, short circuiting it, over temperaturing it. In Ambry's case, we take a single cell and we apply it to each of those 3 tests. And we can show that before the test, the battery cycled in a certain efficiency, in a certain amount of capacity. And after those tests, it was unaffected by those abuse tests. And this is a single cell without any electronics protecting that cell, unlike a lithium ion module, which is usually required significant electronics in order to protect those cells from this type of test. So very robust tolerance to abuse without any safety events happening as a result of that. And now we are bidding on projects today which align with our production schedule. We are typically stacking these containers on top of each other because we don't have HVAC systems, ductwork to prevent that. We also don't have safety issues that prevent a container being below another container. So we will typically package up a bunch of containers, typical lithium ion inverters, a transformer to make a power block, and then we will array power blocks on a larger project. This happens to be a 300 megawatt, 1.2 gigawatt hour project, which Ambry was awarded in South Africa. So you can see it occupies about 7 acres or about 2.8 hectares of space, which is along the lines of the type of footprint that lithium-ion requires for projects of this size. So it is a fairly space-efficient technology for these types of projects. And then lastly, just want to share Ambry's production roadmap. So we are producing cells and prototypes in our headquarters in Marlborough, Massachusetts. We are building out a pilot production facility that I referred to earlier, also in Massachusetts. We'll generate our pilot systems, and then our high volume manufacturing plant later also in the United States, planned to be commissioned in 2025. Will produce the volumes that you see here at the bottom of the page. And that's the total of my presentation. I appreciate everybody's attention. Happy to take any questions if anybody has them.
Thanks, Adam. That was great. We do have a couple of questions in the chat. I'll read them out. There's a mention of the UL 1973 certification that you talked about, but does Ambry also have goals to pursue UL 9540 sub-assembly certification for the DC block?
Yeah, so, we've learned a lot about UL lately. The 1973, as I said, was passed at the cell level. We have also performed the testing for UL 9540A at the cell level, and we haven't been certified yet, but we did pass all those tests, so that certification is forthcoming. It is generally true that if you pass it at the cell level, then building a system doesn't introduce any other additional risks. However, Ambry does plan, as we build next generation systems, to submit them for 9540, 9540A testing, which again, as we pass it at the cell level, is really zero risk that we will fail it at the system level.
And are you able to provide a target price for 1 megawatt-hour container, assuming a large enough order of 50 containers or more, just to understand where it's going?
Yeah, so I'm going to give a little bit longer answer here so that everybody understands how to compare technologies. Of course, it is often quoted what the price is per kilowatt hour for any given technology. That is typically referred to as installed energy pricing, meaning if you take 100 megawatt hours of Ambry batteries and 100 megawatt hours of lithium-ion batteries, you can compare the price there. But that's not real life. So real life is that the project desires 100 megawatt hours of usable energy. And in each case, that has distinctions. So in the case of Ambry, as I said, we've got a 5% guaranteed maximum degradation over 20 years. So we would typically oversize the installation by 5% in order to ensure over 20 years that if there is 5% degradation, that we would still deliver, in this case, 100 megawatt hours at the end of 20 years. In the case of lithium-ion, there's a couple reasons to oversize more. So a lithium-ion system typically is going to degrade by 30 to 50% over the life of 20 years. And therefore, it will nominally start with a 10% oversizing in order to essentially manage through the degradation of the first 3 or 5 years of usage. And then each 3 or 5 years, it will be more batteries will be added to that system. So we call that augmentation, in order to essentially enable that battery system to last for 20 years and still deliver 100 megawatt hours over that period of time. So from a CapEx perspective, you've got a 10% oversizing from day one. Second thing associated with lithium-ion is typically doesn't like to go from 0% to 100% to 0% state of charge. Most recommendations are somewhere between 5 and 95% or 10% to 90%, depending on the supplier. So there's also more capacity is needed in order to overcome that essentially derating. And so there's usually another 5 or 10% on top of that. So that means if we're going to compare at the CapEx level to technologies like this, we need to take in those things into consideration. Lastly, the cost of that augmentation I referred to is obviously not free. We need to estimate what the price of lithium ion is going to be 3 to 5 years from now, and then each 3 to 5 year segment from then on through 20 years, and factor that into future costs. So that typically shows up as an operating cost, and by far overwhelms all the other operating costs that are factored into an energy storage system. So Ambry has zero in that category, and so that there's a huge advantage there in terms of operating cost over the lifetime of an energy storage system. But to get back to your answer, our price right now for the scenario that was asked, it's about $200 per kilowatt hour for a fully populated container shipping out of our plant in 2025 or later.
Great. 2 more questions. One is, what efficiency losses are seen in operations in cold climates?
Yeah, good question. So these batteries are well insulated inside the container, and they generate, as I said, their own heat in order to maintain their operating temperature. The difference if we're operating in an extreme cold environment is that the frequency of operation or frequency of cycling would need to increase somewhat, not a huge amount, but it's kind of straightforward, right? If you take an icicle and you put it outside on an 80 degree or a hot summer day, then it's going to melt faster than putting it out on a day that's closer to freezing. In our case, in extremely cold temperatures, more heat will be lost through the insulation than we would on a warmer day. So that means there is no degradation in terms of capacity. The batteries are always going to be at their operating temperature. The only thing to watch out for is how much idle time between full cycle or between usage is necessary in order to keep that battery at its operating temperature. Now, those heaters always exist inside each container and can always be deployed or always be used in order to maintain the temperature if the usage of the battery doesn't keep up with what's necessary in order to maintain its operating temperature. So, if there's a coldy day, if it's a cloudy day, or there's no solar to be used, and there's no desire for the battery to be cycled, always energize those heaters and keep the batteries warm. Typically, we don't expect that to happen because no matter what the scenario, batteries always can make money through arbitrage by charging at the lowest cost price of the day and discharging at the highest price time of the day. So whether that's solar energy or not, these batteries can be used to make money, and that's typically why people install batteries in the first place.
Great. The last question: what are potential supply chain challenges for your products?
Yeah, so a bit unique in that these materials are not typically seen in other people's batteries. And the thing that it works in our favor here is that, 2 things. One, Ambry is the only one making batteries essentially with these materials. The second thing is none of these batteries are going to go into EVs. So we're not competing with EVs for the availability of these materials. Calcium is the 5th most available element on the planet, so that's a completely non-issue. On the other hand, antimony is along the same amount, about the same amount of quantity on the planet as lithium. However, and like lithium, actually, antimony is available in about 12 countries around the world. It is available in the United States in a mine in Idaho, which is in the process of being re-permitted because it was dormant. It's been dormant since 1990. There are available antimony in Mexico, Canada, Slovakia, Turkey, South Africa, Australia, number of friendly countries. However, there is a significant amount of it that either comes out of or touches China from a processing perspective. That percentage has been dropping over the last 5 to 10 years. And as we see more processing coming out of countries like Oman, Singapore, Thailand, then the percentage that's touching China has actually been dropping considerably. So that's the only thing that we keep an eye on. We do know how much antimony we will require in order to achieve our business plan, which is quite aggressive. Again, no competition is expected from EVs nor from other battery companies. So therefore, we basically have control over that situation.
Great. Yeah, great. Thanks so much, Adam. That was a great presentation, great questions coming in. So thank you for presenting today. I'm going to now hand it over to Jeffrey from Invinity. Jeffrey, if you want to come on video and pull up your slide, we're ready. And then please keep the questions coming. And we'll ask Jeffrey his questions after the presentation.
Thanks a lot. Can you hear me okay?
Yep.
Everything good. Let me just fire this up. Can you see this now?
Yes, we can see your screen.
Excellent. Good. Cool. So yeah, again, thanks, Elos Council, for having us on. Very keen to kind of show where we're at with our technology. I'll be telling you a bit about kind of the product we've got today, a little bit about the fundamentals of the chemistry, how this thing works, and how that we see that differentiating ourselves in terms of performance. Then moving on a little bit about where we see that fitting into market. So why is that performance relevant to developers, PPA providers, governments who want to decarbonize, that kind of thing, and to close out with a bit of a kind of view to the next step for Invinity's product, where we see ourselves going, and kind of near-term plans following on from the systems that we've got installed and how they're doing date. So to kick off, yeah, so we are Invinity Energy Systems. We develop, manufacture vanadium redox flow batteries. So this is a symmetrical, all liquid redox flow battery. So that means the juice in both tanks is the same composition. So you've got 2 tanks of electrolyte, which stores the energy containing, or the energy storage fluid. That's separate from, if I can get my mouse up here, yeah, down here. So it's separate from a pair of pumps, which then circulate the electrolyte through 2 sides of cell stacks. So this is kind of the basis for our product that we've been deploying for the last few years. We are kind of using this as a platform to move towards bigger utility scale applications. So what this looks like behind the hood is doing redox chemistry within this kind of central stack portion. So this is the power module, if you like, the power section. So you have cycling independent loops, 2 independent loops of electrolyte, and during the charging, the diagram on the left, you have the +5 oxidation state being generated, pushing the redox balance of each tank further apart, and so that kind of generates this the voltage where which you can use to discharge that difference in redox potential between the 2 tanks. So yeah, so similar to what we had before. So part of the all liquid nature of the chemistry that we're using here contributes to basically avoiding some of the degradation type processes that other chemistries, other technologies see. So we're able to use the products at a much higher capacity, much higher performance for much longer asset lifetime or project lifetime. So I'll come onto that a bit more in a second. Another part of this, the relevance of this specific chemistry being it's aqueous, and yeah, so I guess given what we've heard just now, it's low temperature. So this is it's a room temperature, let's say, chemistry. You can operate between -5 and 45 degrees operating temperature, external temperature. And so what does that mean in terms of a product? So yeah, we're turning this into systems for behind the meter applications and front of the meter applications. So also as mentioned previously, we've got good safety record. We have nothing that catches fire, nothing that causes thermal runaway. So we've been through our UL certifications, and try as they might, they couldn't set us on fire, which was part of the part of the outcomes of the report. Yeah, long life. That's a part of how we can achieve, how we can demonstrate a lower levelized cost of storage. So that's relating to the previous technology as well. This is relating to the kind of long-term asset type model as opposed to a shorter lifetime degradation type business model. We've got increasing number of assets deployed, which I'll come on to in a sec as well. Recyclable factory build. So factory build is something that we've focused on as a business, as a kind of business strategy. So trying to enable us to leverage the learning curve, the cost reductions that come along with lots of experience manufacturing, high numbers of modules, high number of units, so we can kind of leverage the leverage scale to help us deliver economic products. This one of the things I've mentioned a couple times now is this kind of long life. This is the obligatory accelerated cycle testing slide. So yeah, we've been running tests for a few years with accelerated duty cycle type tests where we charge and discharge these modules as much as we can, and looking for signs of capacity degradation. So we're still looking for that. And so how does that kind of come out in terms of economics? So we're looking for kind of 25+ year use cases that look for kind of stable performance across that whole project lifetime, using that as a basis to stabilize renewable generation, to stabilize grids as standalone storage applications. So coming on to kind of what we expect to do with these batteries, or how these batteries play in markets, or how these assets add value. We see there being kind of a huge range of applications that all sorts of technologies can get involved with. In this diagram here, you can see on the bottom left, we see pretty much the kind of things that energy storage is doing on grids today. So that broadly 1 to 2 hours, some exceptions in California, hundreds of cycles, low single-digit hundreds of cycles per year. So a lot of this stuff, assets doing, kicking off with Hornsdale in South Africa, have been frequency response services. So that's very low throughput, lots of very shallow cycles, that kind of thing, backing up the grid. So where we see increasing amount of work happening, increasing volume of, increasing size of a market emerging, is in redispatching renewables, doing, longer daily cycles, multiple cycles a day to match supply and demand in real time. So this is an emerging part of what batteries are getting used for on grids. And so this is where we expect that variable cost of degradation to, that we lack, to be a significant driver of value. So as mentioned in the previous presentation as well. So I'll leave that one there. So we've got, so you can see we've kind of categorized a few of these zones, you could say, of what needs doing and how you can categorize them. And so we've been doing pilot studies in these areas in different, with our current technology in different countries. So top left, we have a project which is looking at delivering resilience to a stressed portion of the California grid. So this is focused on mitigating the impact of wildfire-induced local network outage. something that requires a longer duration capacity. On the top right, there's some local renewable generation self-consumption, maximizing zero carbon energy for a utility. So this is kind of helping get closer to their net zero goals. Again, something that requires at least a cycle a day, with both grid and solar charging. Bottom left, this is a very, very high throughput application. This is a coupled hydrogen generation project looking to firm renewable generation to feed electrolysis to kind of generate a stable, more economical supply of hydrogen, and looking at how to arrange that in the context of both wind and tidal generation. And the bottom right is our system near Oxford, is currently connected to the grid, doing energy trading, and it will be providing fast frequency response services. So this is kind of the archetype for a standalone grid stability implementation of this technology. So that's been on the grid since last year, and it's been a really useful to kind of the development of our product and where we want to take this technology. So what we're working on currently is kind of expanding deployment, expanding manufacture, making systems in Canada, solar coupled there, a big solar coupled project in South Australia, the middle there, and another Californian project, solar coupled project there, focused on kind of fringe of grid resilience coupled with PV again. So this is kind of taking a variety of use cases, proving them out in now in the near future, and then looking forward to the future of the technology. So where are we going? So we're going to leverage all of this field experience. We're taking a lot of collecting a lot of data on how things are going. You can see here a little snippet from some operational data. So this is showing how we're kind of managing the system of modules, the set of modules that are achieving very close balancing. So there's 54 modules getting dispatched there, and so we're taking a lot of this kind of module level learning, architecture level learning, and feeding that back into our product development process. So we are working with a number of innovation funding parties to kind of develop this product, to get ourselves into a higher commercial readiness and manufacturing readiness. So we're targeting kind of 9s or 10s depending on whose criteria you're using across the board by 2025. This is something leveraging our current installed fleet, working towards architectures which are suited to higher scale installations. So really targeting that 50, 100, 200 megawatt scale deployments. That's work that we're using the kind of power electronics experience of Siemens Gamesa to kind of integrate a full AC site package that we can end up bringing to market. So some strategic partners we're working with there to solidify the supply chain for key strategic components of our technology. And there's a bit of kind of goals in terms of performance targets you can see on the bottom left there, as we look to scale up into the larger scale applications, larger scale deployments. So kind of that's a bit of where we kind of about the technology, where we expect it to play. A couple examples of what we're doing today, where our boots have hit the ground, and this last bit is a bit of where we're going. If any of this sounds like something you could deploy in the next few years, please get in touch. This is my email address, and always happy to take inquiries and any questions that you've got now. Be happy to answer them now as well. Thanks for listening.
Great, thanks, Jeffrey. That was great, and it's great to see the application in really globally all around the world. Phil, if you have any questions for Jeffrey, if you have questions about Invinity, please feel free to put them on the Q&A feature. In the meantime, I have a few questions. Are there any manufacturing or supply chain challenges that you're seeing or foresee in the near future?
Yeah. So yeah, very similar to the previous technology actually. So we have, let's say, a non-automotive technology or non-automotive chemistry. So we don't have any issues there. So vanadium is much more readily used in the steel industry. So the volumes of vanadium that are produced globally are large compared to the volumes of vanadium that are consumed by the energy storage industry today. So that's something that we have lots of room to expand into. So yeah, here we go. There's production in South Africa, United States, Canada, Russia. So we have partners that supply vanadium in the UK that do processing here in the UK, where I'm currently. We have vanadium production partners that are in further down the supply chain, both in the US and in South Africa. So that's kind of not an issue. The biggest issue we've had to date was actually kind of a very broad issue that a lot of people have, which was the power electronics. So something that all electrochemical energy storage is subject to is lots of power electronics to do voltage regulation, voltage control, DC-AC, wave function conversion. So that we've had some problems alongside everyone else with the lead times for these items, and that's kind of one of the things that we see that we're kind of keeping track of.
Great, thank you. Let's see, I'll just go to the questions. What application do you see beyond 8 hours, as lithium can handle that duration today?
Yeah, so I think lithium definitely can handle that duration. I think there's so my cell phone's a lithium battery. It can handle 48 hours, but during that 48 hours, it does very little. So I wouldn't. So while we would see the differentiation matters for the duration, I think that's more to do with what you're trying to do. So if you want to have your asset stay at a certain state of charge, to be ready to do grid stability services, maintain balance in the system, or mitigate the effect of outages, lithium's great. What we see being a differentiator is the throughput, is the cost to the lithium product of doing work, of cycling frequently, cycling deeply. Is something that was brought up in the previous presentation as well. So I completely agree. Lithium can do 8 hours, but what is more expensive for it to do is heavy lifting. So we want to do that heavy lifting all day, every day.
Great. Yeah, and I'll combine these two questions, kind of looking at your global presence and global strategy. Will you be accelerating your presence in the US due to the Inflation Reduction Act? And do you think China will dominate vanadium flow battery supply chain over the coming years?
So the first one, yes. So we have a couple applications in with various US government funding bodies as part of the projects to kind of increase our manufacturing in North America. So we already have a base in Vancouver, which does some of our kind of core IP manufacturing. And so expanding into the rest of North America is definitely something we expect to do in the near term, to not least benefit from IRA type subsidies. Yeah. So then the second question, do I expect China to dominate VFB supply? So I don't know of much VFB supply coming from China. I think that there is a big VFB in the news in China. Now, whether or not that's a big source of, do we think that Chinese manufacture is a big competitor of ours in our core markets? No, I think that's fair to say. I think that's do we see them competing with us for opportunities? Not particularly. No.
Okay, interesting. What is the target installed cost per megawatt hour for 50 megawatt hour or more?
Yep. So very, very much in line with the previous answer to this question. So that's something that we're doing projects. We're happy to talk to people about what our products cost, because we can get people to buy them. So please get in touch with your project and we will figure out why VFBs or how a VFB would work from an economic standpoint. That's a lot of what I do on a day-to-day basis. Yeah, so this is something that we are constantly working with, and yeah, get in touch.
Okay, and last question, how will you achieve a 15% increase in round trip efficiency?
Sorry, could you repeat that?
How will you achieve a 15% increase in round trip efficiency?
Yeah, so there's part of what is going on in the system, both from a balancing and a power, working power architecture sense. So there's a simplification that we can do within the power systems architecture that results in, or let's say, how much can I say? Optimizing the power delivery portion, right? So it's kind of keeping along the core technology, along the lines of the same core technology, but optimizing the way that's the power is generated, and the kind of path from redox difference to a high voltage AC. So kind of focusing on that power transfer chain and optimizing that. That's where a lot of the losses are going to come out. There's some of it, efficiencies coming into kind of aux losses, right? So auxiliary consumption is something that is less well attended to, and something else that kind of comes into broader project economics or product use case specific stuff. And so there's the majority of it coming from the kind of the power chain, charging and discharging, and a small portion of that's coming from aux consumption, reduction.
Okay, well, thank you, Jeffrey. We're running out of time, so thank you, Jeffrey. Thank you, Adam. Great presentations and great Q&A. So we'll be wrapping up. I know we couldn't get to all the questions. If you do have more specific questions, if you have questions about your particular project, feel free to reach out to our speakers. And I'll also share the recordings and the contact information. We do have the technology sharing sessions every month on the last Wednesday of each month. So stay tuned for the next one coming up in April. And again, thank you so much, Adam and Jeffrey, and thank you everybody for joining today.
Thanks for coming. Thanks for listening.